My name's Nika Durham. I'm from the National Renewable Energy Lab, and just want to welcome you all to today's webinar on NREL's 2017 Annual Technology Baseline on the cost and performance data for electricity generation technologies. Before we get started, I'll introduce you to today's panelists. With us, we have Energy Systems Modeler and Analyst Wesley Cole with NREL's Forecasting and Modeling Group, as well as Senior Engineer Maureen Hand with NREL's Techno-Economic Analysis Group. Maureen and Wesley will be discussing technology-specific information on a broad spectrum of electricity generation technologies, including wind, solar, geothermal, hydropower, biomass, coal, natural gas, and nuclear, showcasing current and projected data from various sources. And with that, I'll pass things on to Maureen to introduce the presentation.
Thank you, Nika. I'm happy to be here today to talk to you about our 2017 Annual Technology Baseline. As the name suggests, this is a product that we update annually, and this is the third edition of this technology baseline. As you can see, there are a number of contributors from a number of my colleagues here at NREL, as well as Oak Ridge National Laboratory. So it's as this big team that we assemble all of this information together. Today, I'm going to talk a little bit about the ATB project, some of the background and methodology. In particular, I'll talk about how we develop our base year estimates, as well as our future year projections. I'll provide some information about the cost and performance summary data that we've assembled this year. And then my colleague, Wesley Cole, will provide you with a preview of the 2017 standard scenarios. One of our primary objectives with the Annual Technology Baseline, or ATB, is to provide a transparent set of electricity generation technology cost and performance. There are a number of technologies that can be used in the United States. We try to capture the various ranges that you might see, particularly associated with resource characteristics for the renewable technologies, associated with fuel price assumptions for the fuel-based technologies. And we try to capture these things for costs of technologies today and through 2050 in a very transparent way. And you can see all of the technologies that we are currently including in the ATB listed on the slide. We produce two products under the Annual Technology Baseline. The first one is a web application that details all of the technologies, the methods, and assumptions that we've used to create the projections. For those of you who've been following our work in the past, this web application now replaces the PDF document that we used to have. And I hope you'll find it a more useful way of accessing the information. In addition to the web application, we provide a spreadsheet that includes all of the specific technology inputs for the base year as well as future year assumptions for all of the electricity generation technologies. And then, as in the past, we still have an associated product, the Standard Scenarios Report. And in this report, we use the ATB technology assumptions to explore a range of options for the electric sector, a variety of scenarios about how the electric sector might evolve. There's a number of different ways that the ATB is used by other people. Certainly, we use it here at NREL for a number of our studies. But there are utilities and system operators that have used the ATB. Academic organizations are using ATB. Some policy analysis for national as well as state governments have used the ATB. And even some international organizations are relying on our ATB information, as well as, of course, the Department of Energy, the primary sponsor for NREL's work, and for this work in particular. The basic format for each of the technologies includes a number of topic areas. We overview the technology and the resource that's available. We look at the capital costs, or CapEx, for the base year estimates and projections through 2050. We have another section where we define what is included in the capital expenditures because we're trying to establish a consistent way of looking at capital costs for all the technologies. There's a section that explores the operation and maintenance, or O&M costs, again for the base year and estimates through 2050. We look at the energy production for the technology in terms of capacity factor. And we have a section that describes the methodology that we use to develop future cost and performance projections. And we try to compare the ATB projections with other sources of future cost and performance. And then finally, we compile or depict all of these changes to capital costs, operating costs, and energy production in terms of levelized cost of energy as a way of seeing how the overall technology changes can be combined. And as I go through the next slides, we'll be looking at some examples from each of the technologies, but you can find similar images for all of the electricity generation technologies in the ATB web app. We create representative plants for each of the technologies in order to explore some of the ranges that you might see. In particular, for the renewable technologies, the ranges that you see are driven often by physical characteristics. For example, we create 10 representative plants for land-based wind, and those 10 plants are distinguished roughly according to the annual average wind speed that you might find at those geographic locations throughout the United States. In some cases, for example, the fuel-based technologies, we look at different kinds of technologies, different configurations for natural gas or coal plants, for example. But in addition, we illustrate two different capacity factors that might be relevant for the U.S. electric sector. This slide shows an example of the kind of information that you would see for one representative land-based wind plant that we call TRG4, or Techno Resource Group 4. So these are the capacity factor, capital costs, operating costs, and levelized cost of energy associated with wind plants that might be sited in locations with about an 8 meter per second annual average wind speed. For each of the representative plants, we include the three primary cost parameters and an LCOE, combined LCOE estimate. But we're trying to look at how these technologies change in the future through 2050 in terms of high, mid, and low cost projections. So we've defined these high, mid, and low cases generally or generically according to the descriptions on the slide. We've kept the high case is assuming that there's essentially little or no change to the technology from today out through 2050. The mid case reflects continued industry growth, public and private R&D investments, and market conditions that may be characterized as likely or not surprising. And the low case is intended to explore the limit of surprise, not necessarily the absolute low bound, but a very aggressive projection for the renewable technologies. And the purpose of these high, mid, and low cases is to provide a range of future outcomes to understand how the electric sector might be different according to different future technology cost and performance projections. The base year estimates, and in this year's ATB, the base year is 2015, because that was the last full calendar year for which we had technology information when we began assembling this data. For the renewable technologies, we combine bottom-up cost modeling with market data reports or market data estimates in order to try to explore the base year estimates in terms of actual installations in the United States. For the fuel-based technologies, we do continue to rely on the annual energy outlook produced by the EIA every year. This is an example from the utility scale PV plant section of the ATB web application. This is showing the capital expenditures, and we are illustrating historical trends, the current estimates or base year estimate, and future projections. And you can see how in the base year estimate for 2015, that we are providing an estimate that is similar or based on the historical data for installations in the United States. And then you see the projections for high, mid, and low future technology advances. And again, we have similar images for the other technologies. We do something a little bit different for the fuel-based technologies. In this case, we compare the ATB estimates with estimates of the cost of new generation plants, or capital costs of new generation plants, from a number of other organizations. And so the purpose here is to provide some context for the estimates we use in ATB to help people understand how they relate to perspectives that other people in the industry have. When we look at energy production, we do it in terms of capacity factor. Here's an example from the land-based wind plant section of the ATB. And what we're trying to do is estimate what a new plant installed in the year shown on the x-axis, what a new plant might produce each year over its lifetime. Similar to the capital cost, we try to look at the historical performance of all electricity generation technologies in order to illustrate how the estimates of our base year compare. But it's important, especially for the renewable technologies, to recognize that we're trying to illustrate the potential range you might see throughout the entire United States, or the resource across the United States. Whereas in the real world, most of the wind plants are installed in higher wind locations. So you don't necessarily see plants installed in all regions of the United States. And for this example, for wind, it's the TRG4 area where most of the wind plants are installed today. When we look at our future cost and performance estimates, there's a number of methodologies that can be applied. And we try to explore a number of different ways of looking at future cost and performance. And we also, as I mentioned earlier, compare the estimates that we create for ATB with other literature about future cost and performance. So, and we do this for the renewable technologies. There's a number of different methods that can be applied, and we rely primarily on published information to do this, but things like expert elicitation are often used to provide a formal, structured way of gathering information about future costs. We do rely on literature surveys. There's a number of publications that produce projections of technologies, and we can often use the statistics from those surveys, looking at, say, the median of that population as a way of developing our mid-cost projection, for example. Pathway analysis is another way of looking at how specific technology innovation opportunities can affect your costs. Expert input is one method of confirming that your technology pathway analysis is based on ways that other experts see the technologies changing. And then learning curves or learning rates are another way of looking at how technology might change over time based on deployment projections. So when we create all of these different projections for the technologies, we compare them with other published literature. Here's an example from the hydropower section of the ATB. And this shows in blue the ATB projections for mid and low cost cases for non-powered dam technologies, as well as new stream reach development technologies. And the gray lines are showing projections from other published literature. So this helps to give you a sense of how the ATB projections relate to what other perspectives might be out there in the industry. Now, as I mentioned, in ATB, we're really trying to focus on the capital cost, the operating cost, and the capacity factor for the renewable technologies. It's difficult to understand how each of those three aspects combines to give you an overall cost of energy. So we do produce levelized cost of energy projections. And in this year's ATB, we've included three different ways of looking at LCOE. In the geothermal plant example shown on the slide, you're seeing the normalized LCOE. And this approach simply allows you to really focus on the difference between the high, mid, and low projections for the technologies, the different technologies that are represented, and the range of resources that we see in the United States. We did calculate the LCOE using two different market conditions, and I'll speak more about those later in the presentation. For the fuel-based technologies, we do a somewhat different approach in that we are relying on the annual energy outlook from the EIA for the base year costs and the future year projections. The fuel-based technology future year projections are largely driven by assumptions about fuel prices and how those might change over time. So when we put all of this together, you can see the base year 2015 LCOE ranges. And remember that the ranges that we're showing here for the renewable technologies go across the entire range of resource that you might see in the United States. The ranges for the fuel-based technologies are based on the representative plants that we include, and primarily are based on the different capacity factor assumptions that we use to illustrate how the cost of energy might change. And again, LCOE is a summary metric. It's not the focus of this work. But what we want to try to illustrate with these LCOE slides is how things could change over time, how the relative cost of energy of different technologies might vary over time for our low, mid, and high projections. So this slide is showing the projections for the year 2030, and you can see that for the renewable technologies, as we look at the low and mid projections, we're starting to see a tighter range across the resources, and the overall magnitude of the cost is reduced. These LCOE estimates do not include any incentives that could be available today or in the future, things like a production tax credit or investment tax credit. And the example that you're looking at here is based on current market conditions. Again, I'll speak more about that in a few minutes. And then as we go from 2030 to 2050, you see the same trends continuing. The range is tightening. The overall magnitude of the LCOE for renewable technologies continues to decline. So we added a section to the HEB this year to talk about how different project finance parameters can affect your overall cost of energy. We created two basic scenarios, one that looks at current market conditions, and this one is based on debt interest and return on equity rates that are reflective of the year 2017 in the annual energy outlook. Now, we also have a set of conditions that we called long-term historical conditions, and this reflects debt interest and return on equity rates that you might have seen in the fairly recent past. And these are the same rates that we have used in our past editions of HEB, as well as in our Reeds modeling and the standard scenarios model results. Now, in the graph that you're seeing on this chart, we're also showing for those renewable technologies that today in 2015 have the production tax credit or investment tax credit available to them. You can see the impact of that in the blue bars. So the project finance parameters, or the debt rate and return on equity, is a very significant driver of the cost of energy. As you can see from the gray, the historical market conditions, to the green, the current market conditions with lower interest rates, and the blue where the production tax credit and the investment tax credit are included. Another parameter that is significant to understanding the levelized cost of energy is the economic life. And in the case of the HEB, we have defined the economic life to be the period over which the project capital cost is amortized. In this graph, you're seeing two different assumptions about economic life. In the green bars, the economic life is 20 years for all technologies. So basically, this represents the perspective of a single investor, perhaps, who is looking at a 20-year investment and looking across all the different technologies. The other assumption, or the gray bars there, are showing where the economic life is equal to the technical life of the project. So each of these technologies may operate for a different number of years. And so that's what we're showing when we're saying the economic life is equal to the technical life. And so again, this assumption can have a significant impact on your levelized cost of energy. Here's a screenshot of the new web application. And again, I'm hopeful that you will find this easier to use and allow you to access information more directly. On the left side of the screen, you'll be able to select any technology or all technologies that you would like to look at. So the electricity generation technologies are on the left. And then on the top, you'll see a way of filtering the content. So you'd be able to look at each of our different content sections, the capital cost, the operating cost, capacity factor, any of those things independently, and then again for each technology that you might be interested in. At the bottom of the web app, there's a number of different links that show some of these cross-technology information. So the project finance sensitivity that I just discussed, the cost and performance summary, those kinds of things are in that bottom footer content. And finally, as we begin to think about next year's annual technology baseline, some of the things that we are considering as improvements will be to enhance the geothermal representation. There's a new study from the Department of Energy that could provide a number of insights to expand the way we represent geothermal technologies. We're also interested in providing a more detailed picture of the future cost and performance projections using the bottom-up modeling applications that we have here at NREL, and really trying to focus more on the technology advancement aspects of the ATB. And finally, we are considering adding storage technologies to next year's ATB. With that, I will turn it over to my colleague Wesley Cole to give you a preview of standard scenarios.
All right, thanks, Maureen. So we've just talked about the annual technology baseline, which holds all of our cost and performance assumptions for the various electricity generation technologies. So what standard scenarios is essentially a framework for us to take all of those cost performance assumption inputs, take them and put them into our electricity sector market models, and create an ensemble of forward-looking scenarios of the U.S. power sector. So it allows us to look at things like what happens if renewable energy costs stay high, or what happens if the costs come down faster than we might expect in our scenarios. So the standard scenarios framework is a large number of scenarios that allows us to look at a lot of different aspects and help us understand how the power sector might change, especially as we consider different cost and performance assumptions that are part of the annual technology baseline. So this year's standard scenarios report includes 26 scenarios of the electric power sector. So they include traditional sensitivities or levers that we look at, things like low and high natural gas fuel price projections, different levels of demand growth, different amounts of retirements, and then obviously the annual technology baseline cost performance assumptions. We also look at a lot of other scenarios, including low carbon scenarios, scenarios where nuclear technology becomes more cost effective, or scenarios with restricted or reduced transmission builds, scenarios with high penetration of electric vehicles. So we have a wide range of scenarios, and that lets us explore how the power sector might change under a variety of conditions. So the four main areas of focus that we're looking at for this year's work is looking at natural gas renewable energy that's across a wide range of scenarios. They're projected to lead the new capacity additions, to be the primary new capacity that's added to the system. Also looking at the relative competitiveness of wind and PV. So wind has typically grown independent of PV, but both are becoming more cost competitive, and their costs are pretty close to each other in a lot of scenarios, looking at how they trade off with one another. Also looking at storage. We didn't get storage in the annual technology baseline, but we are able to look at that in our scenarios, looking at scenarios with low storage costs and understanding how that might impact the development of the power sector. And then finally, we've got a section looking at nuclear lifetimes. You've likely seen lots of issues related to nuclear plants and challenges with getting the ones that are under construction finished, and challenges with keeping the ones that are already operating to continue to operate. So we'll be exploring some of that and what the impacts could be of nuclear retirements or extended nuclear lifetimes throughout these scenarios. And just like we have in the past, we're going to make our scenario results online. So we have our scenario results viewer, which obviously has last year's results because we haven't yet published this year's results in it. This is a screenshot of that viewer that's interactive, lets you go in and look at a state level for capacity and generation by technology among the different scenarios that we consider, download the data, and do additional analysis to help inform people with the decision making they have. So this process is underway. We're hoping to wrap it up and be able to publish our report in the next, call it 5 to 6 weeks, to have it out there. So that's a summary. This is the scenarios is really complementary to this annual technology baseline work to allow us to understand, instead of relying just on the LCOE to look at how a technology might compare to another, which is an imperfect metric. It allows us to compete the technologies together in a market where there are things like retirements, where we could capture the spatial diversity of renewable energy resources, and where we could do things like capture trade-offs between non-dispatchable and dispatchable technologies. So with that, we'll conclude and take any questions. You can see the ATB website here, where you could go and explore and look at any of the figures that Marina showed in here are on this website. But I think it's a great data set, and we're happy to make it available to everybody.
Okay, well, thanks, Maureen and Wesley, for giving your presentations. We can go ahead and get started with the Q&A session. And I do already have a handful of questions that we can address. As we go, if you have a question, please type your question into the GoToWebinar toolbar under the questions pane, and we'll get to as many as we can. First one I have is, does your data include worldwide information? Can this information be used to estimate technology, financial technology in Africa, for example?
Our focus is primarily on the United States. However, I think that many of the high-level trends are probably applicable globally. We're kind of generally assuming a stable global market for these technologies, especially in the out years. And that could potentially be true for things like capital costs, operating costs, and energy production. Of course, you'd have to make sure that you're looking at similar characteristics for energy production, similar resource characteristics. However, when you're thinking about things like LCOE, your market conditions could be very different from one country to another.
Okay, thank you.
And just the LCOE calculations do depend on you, like they have a maker's tax depreciation, which likely doesn't exist in many other countries. So the financing parameters are specific to the United States. So the LCOE numbers, you wouldn't want to translate those to other countries without doing your own homework there.
Okay. Another question, this is just in general, are the costs displayed as real or nominal?
The costs are all real costs. So if you download the spreadsheet, you'll see it says the dollar year is in the 2015 dollar year. So we're not including inflation in any of the projections.
Okay. And then that kind of leads into another question here. The finance parameters seem pretty low. Can you guys explain how those were developed?
So for the current market condition case, I assume is the one that perhaps seems low. Those were developed using the assumptions or using data from the EIA Annual Energy Outlook in order to calculate for the year 2017 estimates from the AEO, the debt rate and the return on equity rate of return.
Okay.
So you will see, though, that's why we have included different levels of finance or of the financial parameters, the current market conditions represent the kind of a low end of what financing could be and what financing costs could be. The historical you'll see are quite a bit higher, and definitely higher than today's market conditions, but might be represented. It's hard to say, you know, what does financing look like in 2040, which is why we've included both sets of financing parameters. So you could see, one, how financing parameters impact the LCOE, but additionally to just give different sets of metrics for trying to inform any decision making.
Okay. Another question I have, to what extent are future LNG exports and their impacts on NG price volatility built into the AEO projections? How is that reflected through an NG LCOE, if at all?
Yeah, so I'm by no means an expert on the annual energy outlook projections. They do include natural gas exports in their modeling work. I don't know the underlying assumptions or framework for that. So there is some interaction with natural gas exports to the natural gas prices we're using in these projections, but I can't give you any other detail other than there's some interaction. I don't know how significant it is or how much volatility, how much volatility might be included in that.
Okay. Another question I have is, how accurate is the capacity factor used in this presentation?
So it's kind of a broad question, and I'm not clear exactly what it's referring to, but in terms of the capacity factors, so the capacity factors that we were presenting have been compared to historical data. So you can see how the capacity factors that we represent in the ATB compare with historical capacity factors for renewable energy technologies. For dispatchable plants like natural gas combined cycle or coal plants, the capacity factor is largely driven by where you are in the merit order stack, which is why we included kind of a lower end capacity factor, which is the average of the entire fleet, and an upper end, which would represent more of a base load type plant that's operating essentially all the time, except when it's down for outages. So the capacity factors aren't meant to say, here's what the capacity factor of your plant will be if you build this necessarily, but to provide ranges of capacity factors so you understand that for your specific plant or site or location you're looking at, you could get an understanding of what your expected capacity factor might be and how that then translates into relative economics of that plant.
Okay. This question asks, I know the baseline data was from 2015 year end. What would be the progress rate currently from 2015 year end, which is nearly 2 years, especially on renewables?
So for the renewable technologies, you're right that 2 years is a really long time for some of the technologies. They move really fast, and it's really hard to keep up with them. That's part of how we've developed our projections. So as we started this, so most of the projections, we've assembled draft ones early this year. So 2016 data wasn't out yet. We didn't have insights into 2016 data. But you'll see for things like for PV, when we developed especially the near-term projections for that, we only relied on literature that was published very recently because the costs have been changing so rapidly. So we've tried to keep up with things. Obviously, our long publication process doesn't make that easy on our end, but we've tried to capture the rapid change and ensure that if there are anticipated near-term reductions in market or in cost, that we're capturing those in our projections.
Okay, great. Another question I have, will carbon taxes be considered for fossil fuel power sources in the future?
We don't have any plans to include them at this time. And somebody could certainly do that. You'll notice if you download the spreadsheet that everything is there that's used to calculate it. And if you wanted to include a carbon tax, it would be fairly straightforward to do that to see what the impact would be on LCOE. On our end, we're focusing more on the technologies and on the technology improvement pathways, and are focusing less on how things like carbon taxes or tax credits or other things might impact the LCOE.
Okay. Can you explain how the PTC and carbon pricing are or are not considered in the net capacity factors for coal and gas generation? Might be similar.
Yeah, so I guess this goes back to the earlier capacity factor question we were talking about. So for our capacity factors for the fossil units, we are just representing essentially a high-end capacity factor of a plant operating essentially all the time, and one that represents the average fleet-wide capacity factor. So for a specific plant, your capacity factor, especially for a new plant, is likely to fall in between those. If there's a carbon tax, you're likely to have a worse position in the merit order stack and be dispatched less, versus if they're, I mean, it depends on how the market is set up too. So there's a lot of different considerations for how a carbon tax might affect capacity factor. But for our purposes, if you have an anticipated capacity factor of a plant, you could use it to understand how your LCOE will fit based on the kind of average and high-end capacity factors that we've included in the ATB.
Okay. And how do the scenarios limit the total and annual build amounts for wind and solar resource additions?
Oh, that's a good question. So in our scenario modeling, we represent the amount of resource that is there. So you obviously can't build more resource than is allowed. We also represent demand and demand growth. Demand has not grown a lot recently, so there's not a lot of need for new capacity. So unless you could build renewable energy generators for less than the cost of an existing plant that's already been paid off, you're not likely to build it. So it's mostly economics that are limiting new builds, that how fast you might build things. We also capture things like if you build a lot of wind or a lot of solar, you're likely not going to be able to use all the energy. We call it curtailment. You have to turn some of it down or off because you have so much generation during a certain period of time, which obviously impacts economics. So the combination of those factors, in essence, presents a, we'll call it economic bound for how much renewable energy is getting added and how fast it's getting added. Obviously, it changes by scenario. If you do things like lower the cost, you get faster builds. If you have higher costs for renewable energy, you get slower builds.
Okay. Great, thank you. Another question, how do you differentiate between CapEx, FOM, and VOM? Some utilities might utilize CapEx versus VOM for expenditure. Did you rely on FERC Form 1 or some other inputs for these costs?
Well, I'll start, and then Leslie, you probably have something to add to that. So for the capital expenditures, that is representing your initial investment to bring a plant up to commercial operation. Your FOM, or fixed operation and maintenance, is VOM, variable operation maintenance. Those are costs that you incur during the lifetime of the plant. So the capital cost is different from your operating costs during the lifetime of the plant. And
we are using an overnight capital cost, so we're not amortizing a cost of a plant out and then you're making those payments out over time. The capital costs we're representing are overnight, as in you pay it all right away. Your plant is now up and running overnight, and then you're incurring those operation and maintenance costs now that your plant is built and you've paid for it via your overnight costs.
right.
Okay. Great. Next question, why was economic and technical life so short and small for gas CC? Maybe this refers to a slide we can look at.
So gas CC plants, when we do economic life for everything for the 20 years, everything got a 20-year economic life. For the technical life of the plant, we assigned it as 55 years. A huge portion of the gas CC fleet was built in the early 2000s. We don't actually know how long it will stick around. So 55 years is the estimate we're using now. It could obviously change based on how well the plants continue to operate as they continue to age.
Okay. And I have another question that refers to slide 10. The question is, why not have the vertical axis be dollar per kilowatt AC versus as shown?
Yeah, so the PV industry has been operating in units of DC terms for a long time. And so when we get PV reports and look at PV data, they're often reported in dollars per watt DC or dollars per kilowatt DC. So we've presented them in DC terms to be consistent with that. We've talked about converting it to AC because everything else is in AC.
And we do have the same image in AC terms is in the ATB website. You're just seeing the DC version here in the presentation.
Okay, thank you. Another question, how are curtailments developed?
Oh, that's in some sense, a challenging question. Essentially, when we do our modeling, we have underlying hourly data of the different renewable energy generators and how much they might generate, as well as the load. And in essence, the short version is we look for hours of the year where the generation from renewable energy exceeds the amount the grid could absorb. So if your generation exceeds load, or if you can't turn down any of your thermal plants anymore, then they've already reached their minimum turn down level. Or if your transmission is congested, you can't export the energy out of your region, then those all result in any of that generation that can't be utilized being curtailed. So we use those estimates to estimate how much renewable energy we curtail in a given scenario.
And I'd like to just add that in the ATB, we do not make any assumptions about curtailment because, as Wesley's just described, it is very specific to electric systems in geographic areas. So it's within the standard scenarios that curtailment is reflected, but we do not include that in the ATB.
Okay, great. Next question I have, what kinds of energy storage technologies would you consider adding to the ATB?
Well, we would focus on technologies that could be utilized within at the utility scale in the electric sector, probably. We would look at things like pump storage hydropower, some of the new battery technologies that are available, and potentially compressed air energy storage. Those are the technologies that are currently represented in REEDs and in the scenarios modeling. And so it would be useful to improve the transparency of how those technologies are represented by including them in the ATB.
Okay, great. And I have kind of a nice wrap-up question. What do you see as a more significant takeaway from this analysis? Did anything surprise you, any of the outcomes?
So to some extent, ATB is really a project where we're trying to collect information from a variety of sources and assemble it in a transparent way. I think we've seen trends continue generally from last year to this year. I don't know, Wesley, do you want to add anything?
Yeah, I don't know that we have any major things that surprise us, because part of going through this process is that and we do this, the annual technology baseline is an annual thing that we update. So we don't have a lot of time to be surprised in between when we make updates. So I don't know that there's big takeaways, only that there aren't, maybe the takeaway is that we haven't seen any huge surprises. We continue to see things change rapidly. I guess that's a common theme that we see amongst, like, that it is good that we update this every year, because it's easy to get out of date, even by just lagging by a year or two.
Okay. I just got another one. What regional factors are considered beyond capacity factors?
The capacity factors, I think, are the primary differentiations. Capacity factors for renewable energy resources represent the diversity of the renewable energy resource. We obviously don't tie this capacity factor to this location, although we have other work that does that. For the fossil units, there's not really any regional variations, for example, in fuel prices. The only other piece that we've included is regional variation, and we have included the regional capital cost multipliers that we use in our modeling that show essentially what the variation of capital cost is from one region to another. So for example, if you're in a place with union labor versus non-union labor, that could change how much you have to spend on labor. We've just showed the ranges. We didn't include what they actually are, although again, that's in other work if there's interest there. So the focus has been less on regional trends and more on national trends and trying to represent some of the underlying regional variation, especially in resource quality.
Okay, great. Well, thank you. Well, that looks like all of the questions that we have today, and we are just about out of time. So I'd like to thank our speakers for their time. And if you have additional questions regarding the work outlined in this webinar, please contact Wesley at wesley.cole@nrel.gov. This concludes today's webinar. Thanks so much for joining us, and have a wonderful day.